Yeah, we're continuing on chapter 14, which is work energy. And last time we were using this equation here, where this is like the kinetic energy here, the kinetic energy at the beginning, and the work added to the system, and then the kinetic energy at the end. And we'll continue to do some of these problems. We'll take a look at this problem, F14-2, F14-2. If the motor exerts a constant force of 300 newtons on the cable, determine the speed of the 20-kilogram crate when it travels 10 meters up the plane, starting from rest. The coefficient of kinetic friction between the crate and the plane is 0.3. Degrees, 20 kilogram box being pulled up here. And this is 300 newtons pulling it up. And of course, there's going to be friction working against the motion. Remember, friction is always against the motion. And first, probably want to find maybe the normal force. And again, I forget what the book calls it, maybe NC or something like that. And we have this box here. $20 kilograms pushing down. And so if we want to find the normal force, we have to sum the forces. Again, if we go maybe X, Y, sum the force in the Y direction. Again, remember that we want to always consider the acceleration, even though in this case we're not going to have any acceleration no acceleration in the Y direction. So if we use X and Y this way, so no acceleration in the Y direction. So again, if this is 30 degrees, again, if in the Y direction, call up plus. And so you can see that NC minus 20 times 9.81 times cos of 30 degrees going to be equal to 0. And this is plus in this direction here. And then we're going to see the normal force is 169.91 newtons. Again, that's just the way you normally calculate your normal. And so we need to find the work of the force. So let's find work now. And the work of our 300 Newton force is going to be 300 times the change in position. So we started, call the beginning point 0 maybe. They call that S equals 0. So it went from 0 to 10. So it's going to be like 3,000 Newton meters. Now, one thing important, when we're doing work and energy, we're not going to consider, say, the work done by this mass on itself. Remember, in the previous chapter, we always had to consider, like, say, the force of this mass in the x direction. But now we don't do that anymore because the weight takes that into account. So we're going to do the U of the weight. And so remember, that's always going to be the weight times the change in vertical position. So we'll have to see what the vertical change is. So if we maybe make a little triangle over here somewhere, let me put it right here. So it's going to move 10 meters. And so we'll put that 10 over here. We have 30 degrees here. So that means this side over here has to be 10 sine 30 degrees, huh? So it's going to move up this amount. So this is going to be the vertical change. Just using a little triangle. And so therefore, we put this here. So it's going to be the weight. And remember, the weight is going to be 20. And it's going to be minus, right? Because remember, if the weight rises, it's going to be put in as negative. So it's going to be negative. And again, we're using SI units. It's going to be the kilograms times 9.81 to get the weight. So that's going to be the weight. And then the change in Y is going to be that 10 sine 30 degrees. So the work done by the weight is going to be 981 Newton meters. And then we're going to use the friction force. Remember, the friction force is always along the path. So it's going to be like, excuse me, that should be U, sorry. U of the friction force is always going to be the friction force times the path it takes, like the actual linear path. So in this case, it's going to be like delta S. And of course, that's going to always be mu times our normal times the path. And we should remember it's going to almost always be negative, right? Because it's always going to oppose the action, the movement of the object. And our mu is 0.3. Our normal is 169.91. And it's going from like 0 to 10. So delta S will be 10. And it's going to be like around minus 509.7 Newton meters. So I think that's all the work that we have. It's going to be like the force pulling it, the weight, the friction force. And then now the kinetic energy. Once again, you don't have to put all these details and you could just actually put them right into the equation. But at least while we're doing this here, so kinetic energy 1, which is like at the start. Let me say it this way, at start. Is going to be T1 equals 1/2 mv1 squared, but of course that's just going to be 0 because it's starting from rest. So the initial kinetic energy is 0. And at the end, which is T2, 1/2 mv2 squared, 1/2. Our mass is 20, and we don't know what V2 is yet. Like that. And so finally, we have to put everything into our equation. So we'll put work in and kinetic energy. So it's going to be T1 plus summation of the work from 1 to 2 equal T2. And T1 was 0. And our work was 3,000 Newton meters from the force. The weight was minus 981. The friction was minus 507, or 509.7. And T2 was 1/2 times 20 V squared. Now, if you put everything together on the left and divide it by, this is going to be 10 here, and take the square root, you end up getting V2 is 12.28 meters per second. We're going to look at this problem, F14-3. F14-3, notice there's a motor involved and a couple of pulleys. It says if the motor exerts a force of 600 plus 2s squared newtons on the cable, determine the speed of the 100-kilogram crate when it rises to 15 meters. The crate is initially at rest on the ground. (14-3). And we can sort of just focus, we can sort of think of a free body diagram. We're just focusing on that pulley. And it's going to look something like this. And we're told this crate is 100 kilograms. And we're told the force is going to be 600 plus 2s squared. That's in newtons. And so, of course, whatever is on this side of the cable has to be the same on the other side. So those are both going to be the same, basically. And it's going to rise 15 meters. So like you can call maybe S1 is 0. S2 is going to be, call it 12. And it's initially at rest, so you can call V1 0. So we know all those things. And so when we do the work, we know that the weight, the work from the weight, again, is always going to be the weight times delta y. In this case, that's going to be pretty simple. It's going to be 100 kilograms times 9.81 because we're in SI. And we should put a negative in front and put a negative right there. Remember, anytime it's rising, it's going to be negative. And it's rising 15, see, I wrote this wrong here. This is 15 meters. Yeah, fix that up. That's 15, not 12. And when you put this all in your calculator, you get that the work due to the weight is 14,715 Newton meters. Now the force is variable, so we're going to have to integrate, right? So you notice the force is variable. So when we do the U of F, it's going to be the integral, keep some space in the front here. It's going to be the integral from 0 to 15. And there's two forces. Remember, since it's the same on both sides, we can multiply this by 2. But we do have to integrate this. So we're going to have to integrate 600 plus 2s squared ds. 2, we integrate this. That'll be 600s plus 2s cubed over 3. 0 to 15. And this is an s here, by the way. And so when you put those bounds in, and we put in my calculator, I got 22,500 Newton meters. And once again, you can see that the initial kinetic energy, so the energies, the first one's going to be 0 because of velocity 0. T2 is going to be 1/2 mv2 squared, which is going to be 1/2 times 100 v2 squared. Then put them into your formula. Just throw them into that formula there. Again, the initial kinetic energy is 0 plus our work. So we had 22,500 minus our weight, work from the weight, 715. This 1/2 times 100 v2 squared. And we put that all in your calculator, put these together, divide by 50, take the square root. I got V2 was equal to 12.49 meters per second. Any questions on any of that?
Why isn't the work for force, why isn't that negative?
Because you're kind of putting cause let me write that down. It's a good question. It's positive because it's acting in the same direction as the movement. Yeah, that's a good question. Yeah, so it's positive because it's pulling it up this way. Let me show the picture again. It's pulling it up this way, and so of course that's where it's moving. So it's actually contributing to the direction of the motion. So therefore, so like for example, if there was another force, let's say, whereas on the other hand, of course, the weight, you can kind of see. Of course, the weight is always going to be dependent upon whether it's going up or down. But let's say there was another force down here. Let's say there was a force pulling it down this way. Then that would be negative. If there's a force pulling it the opposite direction, let's say if that was in there as well. So yeah, these two are positive because they're pulling it in the direction of motion. Something opposing the motion would be negative, and friction is always going to be negative. Any other questions on that? Okay, good. So let's go on. Again, those are, there's a couple more on there you might want to look at. They're all pretty good. And let me, here's some from the regular sections in the book. Let me pass these out.
Okay.
I want to do the first one now. That I just want to do the first part of it. The second part's easy as well, but it's something from the previous section. So I just want to focus on the current section right now. So let's do. We're going to do 14-5. Determine the required height h of the roller coaster, so that when it is at rest at the crest of the hill at A, it will reach a speed of 100 kilometers per hour when it comes to the bottom at B. Now, so we want to find that height at which it has to start, so that it has 100 kilometer per hour speed when it goes to B. Actually, there's another part of this problem, but we're just going to focus on this part of it right here. This finding this height h. So remember that the nice thing about the weight is all you have to consider is the distance you change vertically. So if you start up here at A and you go down this roller coaster, down at B, and so there's no friction. And so we want to determine the height. Again, so using this method becomes real simple. Again, at V1, we're at 0. And you can call S1, well, I guess we don't really need, we're just going to deal with the difference here. So you can see, once again, so the only work is going to be due to the weight. So the work W is going to begin the weight times delta Y. And in this case, we're dealing with SI. So again, so it's some mass. We don't know what the mass is of the car. So it's some mass, but since it's MSI, it's going to have to be times G. And then delta Y is just going to be our H. So that's going to be the work. Then the energy at T1 is going to be 0 because it's starting a velocity of 0. T2 is just going to be 1/2 mv2 squared, like that. Then just substitute. T1 and the 2 is T2. And again, T1 is 0. And again, the only work done, again, because remember it's going down, so it's going to be positive. Because weight went down vertically. And so that's going to be plus mgh equals 1/2 mv2 squared. And you can see we can cancel the m's, huh? And then for g, we can do 9.81 times h. And we know what, let's see. Oh, sorry. For the, I should have had the velocity v2. So for our velocity, it was given to us, our velocity at v2 was 100,000 meters per hour. And so if we take, let's see, per hour, so if we take 3,600, divide that by 3,600, that will give us our meters per second. So it's going to be 27.77 meters per second. So that's going to be our velocity 2. Remember, if it's 100,000 per hour, and then there's 60 minutes in an hour and 60 seconds in a minute, we can divide that by 3,600 to get this. So that's going to be our second velocity squared. And then just solve for our height, 39.3 more or less meters. Any question on that? Okay. Let's go to 1411 then on your handout. Again, this is really where this is really helpful, because if you're 1411, we're going to take a look at this problem here, 14-11. It says the force F equals 50 Newton is applied to the cord when S is 2 meters. If the 6 kilogram collar is originally at rest, determine its velocity when S is equal to 0. Neglect the friction. See, this is the case again where the force is going to change. The angle of the force is going to change as you're pulling on this cable. So again, normally you would have to integrate. So again, as this angle changes right here, you would have to integrate, because you're only interested in the force that's going to go along the rod. So so you'd have to figure out, like, integrate this with respect to this angle here. But again, because of that rule that we had, we're going to see in a minute, we can simplify this problem tremendously. And again, this is 6 kilograms. And again, we're starting out at 0 via 0 meters per second. And again, remember, this is the rule that simplifies things. So the work of a force on a cable depends only on how far the cable has been pulled. And again, there's probably in this case, probably the easiest way to figure out how far it's been pulled is to kind of measure it from this point to this point. Like say, when it's in this position, it has this length. Then when this collar ends up over here, it'll have this length. So we'll see what this length is here and see what the final length is over here. So again, maybe we can make a little diagram. So initial, so the initial cable. So you can see in this, and where the picture is there, it's just gonna be a triangle like this. And then this is our cable right here. And then this is, and then we know from our diagram, this is 1.5, and this is 2. So if we want to find the length of the cable, of course, it's just going to be 1.5 squared plus 2 squared, and then the square root. So initially, the distance from here to our collar is going to be 2.5 meters. So we might say, so this is, so initial distance from pulley, from the pulley, say, to the collar is going to be this here. And then the final distance, once the collar gets all the way over here, it's just going to be that vertical length, huh? So it's just going to be, so again, in this case here, the pulley was like over here. Once again, the pulley's over here. Now the collar's down here. So then the cable is right here. This is just going to be that 1.5 meters like that. So, you know, the collar was, say, started over here. And so if you want to figure out how far the cable was pulled, it'll be just the difference between this length and this length. So then the work of the force on the cable is going to be, and the force was given as 50 newtons according to the problem. So it's going to be our 50 newtons times our original length was 2.5 minus our final length, which was 1.5. That's going to be 50 Newton meters. And then our energy, T1, once again, we're starting at 0 velocity, so T1 is going to be 0. And T2 is going to be 1/2. The mass was 6 kilograms. And the velocity 2 squared, which you don't know. Substitute T1, summation U1 to 2, T2. We know that T1 is 0. Then the force from on the cable is 50 Newton meters. On the right-hand side, we have 1/2 6 V2 squared. So we have V2 is 4.08 meters per second. See if there's any questions on that. Any questions on that? Oh. And like I said, this is because of this rule up here, this made a very difficult problem very easy, rather than having to integrate this. And we have to integrate as the angle is changing. This makes it real easy. Again, this only works when there's no friction, but most of the problems we're going to use this on, they're not going to have friction. Okay, let's do, I think this one's a little bit long. Well, I probably have enough time to do one more. Let's do 1413. And it's a brick sliding off the roof, a smooth roof. And it's going to get to point B, and that's going to go from B to the ground. We'll have to do this in 2 steps. We're going to take a look at this problem, 14-13. The 2-pound brick slides down a smooth roof such that when it is at A, it has a velocity of 5 feet per second. Determine the speed of the brick just before it leaves the surface at B. Also determine the distance D from the wall to where it strikes the ground and the speed at which it hits the ground. And actually this is, 1413. 14-13. So the block is sliding from A to B. At this time, the block is not starting at 0, starting at 5 feet per second. And the vertical change is going to be 15 feet. You go from A to B, which of course is what we need. And again, VA is 5. And no friction. So again, the work of the weight from A to B. And again, UW. And we're told it's 2 pounds, by the way, 2 pounds. And so it's going to be 2 pounds times 15 feet, which is going to be 30 pound-feet. And again, this time T1 is going to be a half. And again, the mass is going to be 2. Remember, keep in mind, this is English unit, so we have to divide 32.2. And the velocity was 5 squared. And then T2 is going to be 1/2 times 2, 32.2, times velocity of B squared. And so you can just substitute. So T1, the work going from 1 to 2. And again, there's no friction in this case, so. And again, would we say our work was 30 pound-feet? 1/2 to 32.2 VB squared. And you can put that on your calculator. End up with VB equals to 31.48 feet per second. So that's the velocity of B. So once it gets to B, it really becomes a sort of a projectile problem because it's just going to be in the air. So once it's at B, and so what's happening at B? It's going, so it has this velocity here. 31.48. So again, you treat this like as a projectile. And if we figure out the x velocity and the y velocity, so we're given that the roof is 345. So let me put that over here somewhere. So like 5, 3, 4, like this. So that means, so again, our x velocity will be the x value here. So 31.48 times 4/5, and which is about 25.2. And then the y coordinate is going to be 31.48 times 3/5. And I guess we should maybe, since that looks like it's going downward, we'll put a negative there. About 18.9 meters per second. So this is velocity in y direction. And up here, this is velocity in the x direction. So again, just treat it like as a projectile. And again, there's several ways to do this. Maybe the easiest thing in this case is just see how long it takes to hit the ground. So, so do the y direction. Just use your normal projectile stuff. So, and it's, what is that? 30 feet above the ground. So we're going to do like SY S0 plus V0t plus 1/2 AT squared. So just the normal projectile equation. And we want to see how long it takes to drop 30 feet. So again, if we call this our point B, we'll call that 0, 0. And see how long it takes to drop the 30 feet. And again, if we start at 0 and we're minus around 18.9. Minus 1/2, 32.2 t squared. And we'll rearrange everything. It's going to be 16.1 t squared. Again, I'll bring everything over to the left. Plus 18.9 t minus 30 is 0. And you can probably, I just use the quadratic formula. So t was equal to like minus 18.9 plus or minus 18.9 squared. That's 4 times A times C divided by 2A. And when you put into your calculator, one of them will be negative, the other one will be positive, and the positive one is the one we want. And so it looks like about 0.9 seconds. So that's the time to hit the ground. And so, so we want to see what's x doing during that time in the x direction. So again, S of x is going to be S0 plus V0. Remember, of course, from the last chapter 12, I guess, there's no acceleration in the x direction. So S of x is 0 plus 25.2, which we got from up here was our 25.2 times the t, which is 0.9. So it looks like S of X is 22.66 feet. And see, I guess it also asks for the speed at which it hits the ground. Let's see. So we'll have to find that. So let's take a look at that. Now we know the x direction is going to be constant. So that was still at 25.2 feet. It's at feet per second. In the y direction, let's see, v of y is going to be equal to the initial velocity of y. Initial velocity of y plus at, huh? And so the velocity of y is going to be our initial one, which minus 18.9 minus 32.2 times 0.9. And so that's going to be, I think, calculate that. Minus 18.9 minus 32.2 times 0.9. Looks like minus 47.88 feet per second. That look right. So what that's saying is so it's going down like in this direction, this direction. So it's like 25.2. This is 47.88. So then if you want the actual magnitude, so it's like 54.1 meters per second. Does that look right to everyone? Look at that. Now, just real quick, let's just check. We could check this real quick. So if we go from point B, if we apply work energy, could we get the same thing? We'll see here. So if we apply work energy, so U from the work is going to be our weight times our delta Y, and our weight was 2 pounds. 2 pounds, that's going to drop 30 feet, which is going to be 60 pound-feet. And then our initial velocity was 1/2 mv1 squared. Again, this is starting at B. And let's see, what was our initial velocity was 31.48. 31.48 squared divided by 32.2. So that's our initial and V, what was our final point? I don't know what you want to call that final, V final squared. So again, if we use a T1 plus summation of U1 to 2 equals T2, we get 30 0.77 plus our work was 60 pound-feet equals 1/2 to 32.2. Our final velocity squared, so let's see, plus 60 times 32.2, then take the square root. And we get 54.1 again. So we could have done it that way as well. So I think we needed the projectile equation to find the position, but we could have done the velocity either this way, the way we did it, or use work energy. Either way would work.